I'm giving you sample data to use for a binary classification problem. We have true labels, y_true showing whether something actually belongs to a positive class, 1, or negative class, 0. I also give predicted probabilities, y_score. These are the model's guesses of how likely something is to be positive. This data will help you understand how average precision score works. This is a way of measuring how good a binary classification model is. Specifically, sklearn is a popular Python library for machine learning and _average_precision_score is one of its functions. We use it to evaluate models that give probabilities, not just simple yes, no answers. I'm testing your understanding of the average precision score by asking you to choose which statements about it are true. Get ready to put your knowledge to the test. This statement is asking if the average precision score, AP, for the data I've provided will be higher than 0.5. Intuitively, we might think so, because the model's higher probabilities mostly seem to match the actual positive labels, but a precise calculation is needed to confirm. This statement says the average precision score is the same as the area under the precision recall curve. That is true by definition. The average precision score is the area under the curve. If a classifier is perfect, it means it makes no mistakes. In that case, the precision recall curve will be at the top of the graph, resulting in an area under the curve of 1.0. Therefore, a perfect classifier will have an average precision score of 1.0. This statement questions whether the average precision score is affected by having more examples of one class than the other, class imbalance. The average precision score is less sensitive to this problem than some other metrics, but it's still a factor. While it's less sensitive than accuracy, an imbalance still impacts the overall score. These are the actual class labels, y_true, and the model's predicted probabilities, y_score. Remember, higher probability means the model thinks it's more likely the item belongs to the positive class. We use these values to calculate the average precision score and check the truth of the statements. The goal of this problem is to understand and evaluate the average precision score, a metric commonly used to evaluate the performance of binary classification models. This shows the actual class labels for 5 data points. 0 means the data point belongs to the negative class, and 1 means it belongs to the positive class. These are the model's predicted probabilities that each data point belongs to the positive class. For example, the model predicts a 0.8 probability that the second data point is positive. I'd calculate the average precision score using scikit-learn's average_precision_score function. It measures how well the model ranks the positive class instances. The higher the score, the better the model. This statement is absolutely true. The average precision score is precisely the area under the precision recall curve. They are one and the same. That's correct. A perfect classifier would correctly predict every data point. This results in a precision recall curve with an area of 1.0, which is equivalent to an average precision of 1.0. This refers to the true labels, y_true, and the predicted probabilities, y_score, provided to assess the model's performance. This is the list of actual class labels for each data point. 0 means the data point belongs to the negative class, and 1 means it belongs to the positive class. This is a list of predicted probabilities from our model. Each number represents the model's confidence that the corresponding data point belongs to the positive class. The higher the number, the more confident the model is. This is a metric I use to evaluate the performance of a binary classification model. It's specifically designed for situations where I care about both precision, how many of my positive predictions are actually correct, and recall, how many of the actual positive cases my model correctly identifies. This refers to the combined pair of y_true and y_score. They're the ingredients needed for calculating the average precision score. This is the overall goal. I want to understand how well the model is performing, and the average precision score helps me to just that. It's like giving the model a grade based on its performance on this specific dataset. I'm given the true labels, whether an item belongs to a certain group or not, and the model's prediction probabilities for each item. The true labels are 0, 1, 1, 0, and 1. The model predicted probabilities are 0.1, 0.8, 0.9, 0.2, and 0.7. We'll use these to understand average precision. This shows the actual class labels for 5 data points. A 0 means the data point belongs to the negative class, while a 1 means it belongs to the positive class. This represents the model's predicted probabilities of each data point belonging to the positive class. For example, the model thinks the second data point has an 80% chance of being positive. I need to figure out which statements about the average precision score are correct based on the provided data. It's a bit of a detective game. Let's analyze each statement. This statement is tricky. While the model seems decent, based on probabilities, I can't say for sure whether the average precision score will be above 0.5 without doing the calculation. This is absolutely true. A perfect classifier would get every prediction right, which means the average precision would be 1.0, the highest possible score. This statement is correct by definition. The average precision score is the area under the precision recall curve. While it's less sensitive than some other metrics, average precision score is still impacted by imbalanced classes. It's not completely immune to that issue. This shows the actual class labels for 5 data points. 0 represents the negative class, and 1 represents the positive class. I see that there are 3 positive and 2 negative examples. These are the predicted probabilities that each data point belongs to the positive class, output by a binary classification model. For instance, the model predicts a 0.8 probability that the second data point belongs to the positive class. This is a metric used to evaluate the performance of binary classification models. It specifically measures the average precision across all possible recall levels, providing an overall summary of the model's performance by considering many possible classification thresholds. This is the complete dataset. I have both the true class labels, y_true, and the predicted probabilities, y_score, which I'll use to calculate and understand the average precision score. A perfect classifier would assign a probability of 1.0 to every point correctly classified as positive and a probability of 0.0 to every point correctly classified as negative. That leads to a perfect precision recall curve, which has an area under the curve, AUC, of 1.0. Since the average precision is the area under this curve, a perfect classifier will have an average precision of 1.0. Makes sense, right? The average precision score is defined as the area under the precision recall curve. They are essentially the same thing. It's a direct equivalence. Based on the example data alone, it is difficult to definitively say if the average precision will be greater than 0.5 without explicit calculation. While the model seems to do a reasonable job, I cannot be certain. While less sensitive than accuracy, the average precision score can still be affected by class imbalance. If one class heavily outweighs the other, the score might not accurately reflect the model's performance in the smaller class. I'm providing the true labels, YTRUE, and the model's predicted probabilities, YSCORE. These are the inputs to evaluate our binary classification model. YTRUE shows whether each data point actually belongs to the positive class, 1, or negative class, 0. YSCORE represents the model's confidence that each data point is positive. A higher score indicates more confidence. This is the main goal. I'm going to use the average precision score, APS, to measure how well the model performs. This metric looks at precision and recall at various probability thresholds to get an overall score. It's a great way to assess the performance, especially when we care about balancing true positives and false positives. I have provided 4 statements about the APS, and you need to choose which ones are true based on your understanding of how this metric works. Think carefully about the relationship between precision, recall, and the area under the precision recall curve. These are the options that you need to consider from the multiple choices. You'll have to use your understanding to see how well each choice relates to the definition of average precision score, APS. This shows the correct classifications for each data point. A 1 means the data point truly belongs to the positive class, and a 0 indicates it's in the negative class. These are the probabilities predicted by the model for each data point. For example, the first data point has only a 0.1 probability of being positive, while the second one has an 0.8 probability. A higher score means the model is more confident that the data point is from the positive class. I'm given two lists, y_true, which contains the actual class labels, 0 for negative, 1 for positive, and y_score, which contains the model's predicted probabilities for the positive class. Think of it as how confident the model is that each data point belongs to the positive class. Let's analyze this data. These are the correct answers. We'll use these to compare with what my model predicted. These are my model's predictions. For each data point, the number represents the model's confidence that the data point belongs to the positive class. A higher number means more confidence. I need to understand how well my model performed in predicting the positive class. Average precision score, AP, is a metric that helps me evaluate this. While not as sensitive as accuracy, AP is still affected by class imbalance. If one class is much larger than the other, the AP might be skewed because the model might perform very well on the larger class and poorly on the smaller one. And I might miss that poor performance in the smaller class if I don't look closely. A perfect classifier gets everything right. Its precision recall curve would be perfect, meaning the area under the curve, AUCPR, which is the AP score, would be 1.0. The average precision score is exactly equal to the area under the precision recall curve. It's a direct measure of the overall performance of the model across different thresholds of predicted probability. This is tricky. I can't be totally sure without calculating it, but given that my model mostly assigns higher probabilities to the positive class when it's actually positive, it seems likely, but not guaranteed. I'm asked to identify the true statements about the average precision score using what I learned.